Hello all, welcome to the second part of our lecture. This will be the second lecture I'll be recording in this series. I do hope the first lecture was okay and you understood all we talked about. Once again, don't forget the best channel of communication for me is getting to me through the emails or the canvas. Today we'll be talking about scientific notation. As we get into the chemistry classes proper, we'll begin to understand that a lot of things we'll be doing in this class is to solve a lot of problems that are math based, and as a result, we need to review a few important things in math that we need to be successful in this class. Part of those things we're going to be talking about will be scientific notation, significant figure. And in fact, in the last part of this class, I inserted something that will also come up a lot of times, and that is a percentage. And let us get it started. Scientific notation, let us try to understand what scientific notation is. Scientific notation is a convenient way we can use to express very large or very small numbers. At times we have a lot of big numbers, and we'll now begin to see how do we manage these numbers, how are we going to deal with them. Scientific notation offers us that simple avenue whereby we represent number in the form of m times n raised to power n. Of course, the m will be the non-exponential term. The non-exponential term will be that term that will be the term that will be between numbers 1 to 10. But it cannot be 10 because 10 will be a kind of a factor which we're going to use to represent the n. The n will be the exponent. So the exponential term is usually raised to the power of 10 to a whole number exponent, and n can be positive or negative. Of course, we're going to see this as we move along in this lecture. N is usually a positive when the number we're talking about, the non-exponent number, if the non-exponent number we want to put in exponential notation. Okay, let me make this thing clearer. If the non-exponent number is actually, let's say x. If x is less than 1, the exponent is going to be a negative sign. It's going to be a negative. And if x is greater than 1, the exponent is going to be a positive. So if you look at these two numbers, there are a good example I have here. These two numbers, if you look at this now, you find out that this number is a lot of digits here, and definitely you can see that this number is greater than 1. You find out that the exponent here, the exponent we have here is, the exponent we have there is 10. And you see, so that is to tell you that the number is just 10. It is not negative 10. On the other hand, when the number is so small that we start it from 0.000, you find out the exponent is going to be a negative. And that is how you know. So, but what does it even mean? We're going to understand what it means by a standard position of these exponent. What does that mean in the actual sense? The standard position simply means a position to the right or to the left of a first non-zero digit. That is exactly what this simply means. It's the position to the right or to the left of a non-zero digit. I'm adjusting a little bit the size of my screen so that I don't have to so that I don't have to cut anything off. It appears as if I was cutting a few things off, and I want to get that sorted out. Give me a minute. I can easily adjust the size of my screen. That is the beauty of this app that I'm using. I can actually make some little adjustment to my screen, and that is actually very, very interesting. All right, I think I got that sorted out. So what am I trying to say? What I'm trying to say in essence is that the standard position Wait, let me make sure that I got this screen set up very well. I want to be seeing the screen and make sure that nothing is actually missing out from that. Okay. I think I got it at this point. So what that simply means is that, okay, if we look at these numbers now, is that, so the number is actually either to the right or, so let's see. So if you look at this, again, I think this thing either shifted again, but I'm not very sure why it has to shift, you know. So I'm not sure exactly why. It has to shift again. Yeah, it shifted. I don't know. I didn't shift it. So yeah, I think this is exactly what I needed, and I got it completely. Okay. I think I got that figured. I got that taken care of now. Exactly. So like I was saying, sorry for the little bit of delay trying to adjust to the new app I'm using now. It is the Screenomatic app, but it's working out well. So if you look at this, so as I said earlier, the standard position is either to the right or to the left of the first non-zero number that is encountered. It has to be 1, a non-zero number, and then we have to look for the position, the standard position. The standard position can be to the right or to the left. Now, let's look at the example I had previously. The example I had previously shows us that the standard position. Now, I told you that in this case, this number is greater than 1. The standard position is usually to the left. If you look at it now, the standard position will be, we'll keep moving this number. Oh, okay, I have to undo this. That's not what I wanted to do. So if I get my pen and begin to move, we assume that the standard position is here. So if I begin to move this pen, 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This will be the position of this number. And what it means, if I put my decimal here, I will accommodate all the significant digits there, if I'm not asked to round off, and raise it to the power of that. So if we counted 10, and that is why we have 10 at this point. The same thing goes here. You see, this is to the left. When the number is less than 1, the standard position will be to the right, and it's going to be a negative, like I have it there written. So this is going to be 1, 2, 3, 4, 5, 6, 7. So it's going to be 1.0001 times 10 to the negative 7. So again, the significance of the n exponent is that when the value is positive, the original decimal position is to the right of the standard position. So if you look at it, this is the standard position. This is the standard position now. So the decimal will be to the right. So you're going to move it backward. In this one, you're going to move it what? You're going to move it to the right. So that is exactly the meaning of that. So if we now, having known that, we're going to practice on how to write a few examples. I know some of you would have encountered this in maybe in your mathematics classes and all the rest of them. But it's always important for us to review these things so that you'll be competent enough, because we're going to be solving a lot of math problems in this class. In solving this problem, it says express the following number in scientific notation. In my experience in teaching, the problem students make is that they begin to round off the numbers when you are not asked to round off the numbers. I've not asked you to round off any numbers here. What I've just said here is for you to do what? It's just for you to write this number in scientific notation. Do not drop 18 digits, except you are told to round off or drop any digits. So the digit we have here is 1, 2, 3, 4, 5. We're going to maintain our digit. So what we're going to do, the decimal now is not at the end of the number, but it is at this point. So we're going to move this until we get to the standard position, which is this place. So, and then we're going to move it 1, we're going to move it 2, we're going to move it 3. So to write the exponential notation is going to be 8.7 times 10 to, you see, I almost made that mistake too. I have to represent all the numbers. So it's supposed to be 8.7 8.7256 times 10 to the power of 3. And you see here, since the number is greater than 1, the exponent is going to be a positive. Let's look at this one. This is just the opposite case of what we talked about. Here, the exponent, this number is less than 1, 0.0 something. We're going to move it again. So, and we know we're going to have our 7 here. So we can easily start and say, okay, whatever we're going to have will be 7. The first one, 0.29 times 10 to the power of n. We're going to determine what n will be. Let's move this. So it's going to be 1, 2, 3, and 4. What it means is that since it is less than 1, it's going to be to the negative 4. That is the exponent here. And then let's do this one. This one again, if you look at it too, this number, like I said, we're going to maintain all the digits in this case. All the digits here we have that are significant is just the first 3 numbers. These zeros are not significant. So we're going to start by writing it again. So it's going to be 3.89 times 10 to the power of a certain number. Let's now move it. Since you don't see a decimal anywhere, we assume that the decimal is here. So we're going to move. This will be 1, 2, 3, 4, 5, 6, 7. This is going to be to the power of 7. So that is how we do these problems. Now let us move on to the next slide. The problem said the following numbers are written using scientific notation. Write them without using scientific notation. What it means is that we're going to do the exact opposite of what we did earlier. So we're going to now move the zeros back. We're going to move the digit back. So what it means is that this one now is 3.72. That's what we have here that are significant. Let's start moving it. So we're going to move it to the 5 places. And if the digit ends, we'll now begin to add zeros. That is the significant. So if we move this one, it's going to be 1, 2. We're done with this, but now we keep moving. The 3 is going to be 0, 3, 4. We moved 1, 2, 3, 4. We're going to move one more, 0. So if you want to write this number, this is going to be 3720000. And that makes sense. If you move it back, we're going to see this will be, let me use a pointer and see how we move it back. If I have a pointer here and move it back, we're going to have, you see now we're going to have 1, 2, 3, 4, and 5. And that makes sense. The same thing in this one. This one again, now we know that the zeros, because it's the negative, the zeros are going to be in front of this number. So what are we going to do is that I'm going to start in front. And then all these numbers are going to be significant. So they're going to come after the zeros. So we can start with the first one, 0. And then we'll keep moving this. So this is going to move 1, 2, 3, 4, 5, 6, 7. And then after that, what do we have? We now have our numbers. So the numbers are going to be 8, 5, 1, 3. And the best way to deal with this one is just know that when it is raised to the power of a negative, the number of 0 in front of it is going to be the same as to the power it is raised to. Let's count. 1, 2, 3, 4, 5, 6, 7. Okay, this is a little bit more. It's supposed to be, we moved more than we should. So this is 1, 2, 3, 4, 5, 6, 7. So this is one more. I'm going to take one more out. It's supposed to be 7 exactly. So I'm going to take one more. So it's going to be 1 is going to be out here. So what I'm going to have will be 1, 2, 3, 4, 5. This will be 1, 2, 3, 4, 5, 6, and 7. So if you count it, it's going to be 1, 2, 3, 4, 5, 6, 7. Yes. The 7 is supposed to be at this point, but you don't put that in. Or you just count it from 1, 2, 3, 4, 5, 6, 7. That is how that number will be written. So moving on, we're going to start talking about another important concept here, the significant figures. Significant figures or significant digits are so important in the study of chemistry because most times we're going to be solving problems that involve a lot of numbers. So numbers in most of the measurements we take usually constitute a first measurement of certainty and another measurement of uncertainty. What does that mean? Now, if we look at these two, if you look at these two drawings, these are two rulers. The first ruler just have just one marking to represent a whole set of numbers, and both of them are in centimeters. Now, let us try to make a guess at this point. If we try to say, okay, what is the measurement of this lump? We're going to try to find a measurement here. Now, you don't have any marking. That means the only number we can read with certainty will be the first digit. If the digit between this point and this point has to be an estimate because you don't have any marking to guide you. So that estimate number is what will guide the number of digits we're going to write in this. So what that thing means that the highest number of digits I'm going to write for this ruler will be 2 digits. First, I have the first estimate of the first number, which is a certain number, and the second one, which is an estimate. So what that means, let's try to read this. So if you go from here to here, this is 2. This is more than half. Definitely, this is more than 1.5. But it's close to 2. So I would assume that this number will be 1. 1 will be my certain value. Point. It's not up to 2. So it can be 2. I can say 1 point. Okay, I call it, I say 1 point. I assume that this number is 1.9. From these two places, what it means is that this first number is my certain digit. That is the digit that is certain, that no matter how blind I am, I'm going to see that this number is 1 point something. Now, this one becomes the uncertain digit. Now, what is the significance of combining the certain and uncertain digit is that for the measurement of this ruler, I'm going to always have 2 significant figures in each measurement. No matter how bad it is, I'm going to have 2 significant figures in this measurement. Then what about this one? If you look at this one now this one is also a centimeter ruler, but no, it doesn't just have these big markings. You also have small markings that is in 1/10. That is very, very important. Now, we're going to try to take the same reading with this and see what number of digits we can get. Now, I can read 1 clearly. I can also read 1.1. So what it means is that if I'm going to read from here to here, look at it. I can read up to 1 point. You see, if this is 1.9 now, of course. So because each of these means 0.1. So this is 1.9. I can say this is 1.9. Or I can even say 1.8. Right? So let me assume that this is, let me say it's not up to 1.9. So let me call it, the first 2 certain numbers I can get here is 1.8. Because I feel that this stops at 0.8. Actually, this stopped at 0.8 in my eyes. Try to look at it the way you see. So if this is 0.8, but it stopped at it didn't stop at 0.8. So that means it goes beyond a little bit of 0.8. But at least my 0.8, I can read it with certainty. With all certainty, I can read it. Now, it is not up to 0.9. So I'm going to assume that it is between 0.9 and 0.8. So let me say it is in the half of it. So let me say this is 1.85. What does that tell you? It tells you that these 2 digits are my certain digits. I got them from this ruler. I did not estimate them. But the last digit is an estimate. This is a typical estimate of my number. What does that tell you? What that tells you is that, I think I'm going to make this thing a little bit clearer. Now, this is an estimate. An estimate. Now, what does that tell you? What that actually tells you is that I can always express this number into how many digits? Into 3 significant digits. So this is 3 significant figures. Whereas this one, I was able to express it. So a significant digit or significant figure has to deal with the uncertainty in measurement. And that tells us the number of digits we can express any measuring instrument. And this is very, very important as we're going to use a lot of equipment in the lab, including weighing balance, including reading your beakers or reading your gas, your cylinders. We're going to see how this plays out. So what are the rules for significant figures? The managing of significant figures can pose a serious problem to students. And that is why there are convenient rules on how we can count these digits. Now, the first thing we need to know is that every non-zero digit is significant. So assuming if I have this number 2, let's say 2, 5, 3, 4, 2. I don't have any number here that is not significant. What that tells you is that there's no zeros in this number. They're all non-digit. The number of digits in this figure is going to give me 1, 2, 3, 4, 5. It's going to be 5 significant figures. That is exactly what I'm going to get there. Now, managing non-zero digits are very easy and simple to handle. But if we come to managing zeros, it becomes a problem. That is why we have different types of zeros in significant figures. The first one we're going to look at will be what we call the leading zeros. The leading zeros here are zeros that come before any non-zero digit. If you look at the example I have here, these zeros will always come, particularly for numbers that are less than 1 will come before a non-zero digit. These digits are never significant for any reason. They are never significant. So if I have a number as 0.0052, the number of digits I have here will be 2 significant figures because these 0 digits are not significant. Now, some zeros are located between non-zero digits. We call them the captive or the buried zeros. They're the buried or captive zeros. If you look at this one now, you find out that this zero, okay, I'm going to use a different color for the marker here. Let me use maybe red. Look at this. They're buried in between these numbers. These zeros are actually significant. Those buried zeros are significant, provided they are sandwiched in between 2 non-zero digits. The next zeros we're going to be talking about are zeros that come at the end of numbers. If 0 comes at the end of numbers, we call them the trailing zeros. The trailing zeros, we call them the trailing zeros. Now, what is special about the trailing zeros? The trailing zeros have something peculiar about them. What are we talking about them? In the trailing zeros can be significant or not significant. Now, in this case, this number has a decimal place. These trailing zeros in this case is significant because of the decimal point. Now, in some cases where the trailing zeros have no significant point, has no digit, they remain insignificant. So a good example would be, okay, for a trailing zero, assuming I have, let's say, 2000. How many digits do I have here? The number of digits I will have here is just going to be only 1, because these zeros are trailing zeros. They do not have any decimal place. If I had a decimal place at this point, these digits would have been significant. So we call them trailing zeros. So these are the rules governing significant figures that we're going to be seeing a bit. Now, we're also going to see how we can apply the knowledge of these significant figures in mathematical operation. The mathematical operation we're going to be looking at will be the multiplication and division, and then we're going to see addition and subtraction at the same time. Now, in mathematical operations such as multiplication and division, your final answer will have the number of significant digits of the quantities you are multiplying or dividing that have the least number of significant figures. A good example would be what I have here. If you look at what I have here, that's a good example. What I have here, if you see this number is multiplying this number. This has 4 digits. This has 2 significant digits. What it means is that if I do my final answer, I'm going to see a lot of digits, particularly when you use your calculator. Now, you see, the digit your final answer will assume will be the 2 times you're multiplying, the one that has the least number of digits. So this one has 2 digits. What it means is that my final answer is going to assume it's going to be rounded off to 2 digits. That is exactly what I've done at this point. The same thing goes when you're doing your division. I divide this number with this number. This is the answer I get. But because my final answer should be 2 digits, I'm going to round this off to what? 2 significant digits. And that gives me this final answer. So what happens in the case we're doing addition and subtraction? In addition and subtraction, the decimal place becomes precedent. In addition and subtraction, we talk about the decimal places. The decimal places becomes important. So in this case, what are we talking about? So you find out that what we're talking about here is that if we're going to be adding 2 numbers or 3 numbers, the particular number or quantity that has the least number of decimal place will be what the answer will assume. So if you add this number 5.325 and 5.5, we're going to get 10.825. Now, what decides what our answer will be is the one that has the least number of decimal place. This has 3 decimal places and this has 1 decimal place. So at the end of the day, I'm going to make sure that my answer will only have one decimal place. So I'm going to round this off to 10.8. And this becomes my final answer. The same thing happens when we do subtraction. If you subtract this number from this number, you're going to be getting 0.175. If you look again, this has 3 decimal places. This has 1 decimal place. The final answer will be rounded off to what? 1 decimal place. So this will be negative 0.2. So this is how this plays out. We're going to solve some problems to actually understand this after looking at rounding off. So because all these things work together for us to understand how problems are solved in chemistry. In rounding off numbers, this should not be alien to most of you anyway, but we still have to talk about it in case there are some people who are not very conversant with them. Now, in rounding off figures, you are just dropping significant numbers or digits. Now, the digit you want to drop is what decides. So if the first of the non-significant figures to be dropped from an answer is greater than 5, all the non-significant figures that are dropped and then they will be dropped, and the last significant figure that will be remain is going to be increased by a factor of 1. On the other hand, if the number is less than 5, we're not going to increase it. It will remain unchanged. A good example, if you have 10.825 and then we want to round off this to, let's say, 1 decimal place or 3 digits. Now we want to round off this to this. What it means, I'm going to be dropping these 2 numbers. These 2 numbers will be dropped. We're going to drop these 2 numbers. So if you're going to be dropping these 2 numbers, what that simply means is that, okay, drop, I think that's the wrong spelling of drop. I think drop should be, I just want to get the, drop should be D-R-O-P-P-E-D. So if we're going to drop this number, then what I'm going to have here will be, if this 2 was up to 5, this number would have increased to 10.9, but it was not up to, so therefore, my final answer is going to be this. On the other hand, if I want to drop this number again, look at this one now. This is minus 0.175. I want to put it to one place to the right of the decimal. What is going to happen? Now, you see, look at this number. I want to put it to 1 digit. But the number I want to drop is from this number. But this number is 7. That means it's greater than 5. What it means is that I'm going to increase this number to 0.2. And this will be my final answer. So this is what we're going to do as we begin to round off. So let's try to solve some of the problems we see here. I want to know. Okay. I want to be sure. Okay. All right. That should be fine. Let's do these problems immediately. It says round the following to 3 significant digits. We're going to round this number to 3 significant digits. Of course, we're going to try to apply the knowledge of what we just did to 3 significant digits. So let's go. In the first place, we're talking of 3 digits at this point. So what are we going to do? So 9.426 will give us how many digits? That is our problem 3. So it is going to be 19.4. We want it to be in 3 digits, and the number following it is less than 5. Therefore, the number is going to remain. This will give us 9.4. Now, this is an exponential number. It's written in an exponential form. We want it to be in 3 digits. First of all, I'm going to ask you, how many digits do we have here in total? Excuse me, I want to see. There's a problem. I'm trying to find out if I have it here. Okay, I still have the number. I just thought I brought it forward a little bit. So now, again, let's round off this number. It says 1.6300 times 10 raised to the power negative 3 Kelvin. Now, the standard portion of the numbers are not affected in significant digits. We don't touch it. It's not our business in this case. So what we're going to do is to just work on the numbers we see. And this number has how many digits? Because of this decimal here, these 2 digits, 0 digits are significant. So we have 1, 2, 3, 4, 5. So we're not interested. We're asked to make it 3 significant digits. So what we're going to do is to say this will be 1.63. This is 3 digits. times 10 to the power of. We're going to leave this unaffected. We come to this one, 3 digit again. We're going to have 9.86 because 0 is not up to 5. And then we're going to drop the rest, and then we're going to have it to 12. So again to 3 digit, again to 3 digit. Now this one, these numbers here are not significant. The ones that are significant are the ones at the back because of the decimal. So we want this number to stop at this point. You can do this in 3 ways. So I'm going to say I can do this as 0.000. How many zeros? 1, 2, 3, 4, 5. Okay. 1, 2, 3, 4. 1, 2, 3, 4, 5. Okay. 3, 0, 0. Because this has 4 digits, so I'm dropping one of it to make it into 3. Or I can put it in scientific notation to be 3.00 times 10 to the power of course, this will be a negative wave for an exponent. If you count the zeros, 1, 2, 3, 4, 5, it's going to be negative 5. That is what we're going to have there. Now the next one, this is number is greater than 1 to 3 digits. We want it to be at this point. Now, so it's going to be 1 point. No, we're not going to put point. I'm going to write that in the other way when I finish this. So I'm going to say 188. So this is 188. 188, but we're not done. Now, since this number was greater than 5, that's why we increased this to 8. But these numbers, we're not going to drop them. We're going to replace them with what? 0, 0. To maintain it close to this number. Because if you drop this number, it's just going to be 188. And 188 is different from 18800. So it's going to be this, or we put it in scientific notation, 1.88 times 10 to the power of 1, 2, 3, 4, power of 4. And the final one here will be so we're going to want to drop these guys. We're going to drop from here. And since this is up to what? 5, we're going to increase this one to 2.66. So that is the solution to that page. So the next one is going to be exact numbers. At times we encounter what we call exact numbers. Exact numbers are those numbers that have infinite number of significant figures. What does that mean? What it means is that sometimes we solve problems involving equivalence. Those equivalencies are exact numbers. So, and at times I tell students they're just constant. You don't need to mess around with them. Or you can have measurements that are completely exact. Like if you have a dozen of eggs, 1 dozen of eggs is always 12 eggs. These kind of numbers will have infinite number of significant figures. And some of the constant you have in formulas, like a formula to calculate temperature, Fahrenheit to Celsius or Celsius per Fahrenheit, you're going to see this constant. Such numbers are said to have infinite number of significant digits, and we don't actually mess around with them. That's why we call them the exact numbers. So you say in this problem now, we should determine the number of significant figures in each of the following and use scientific notation to express each measurement using the correct number of significant digits. Now in this problem, we are not asked to drop any digit, so we're going to maintain every digit, and at the same time we're going to express it to the number of significant figures. Here we have these two numbers are leading zeros, they're not, so we have 2 significant figures in this number. And then if we want to convert it to scientific notation, it's going to be 3.6 times 10 to the power of -2, because this is a negative exponent when you have 2 zeros in front. For this one, how many digits do we have here? This 0 is a trailing 0, but because of this decimal, it is significant. So we have 3 significant figures here. And for us to write the exponent, we're going to just move this by 1. So it's going to be 1.50. We're not dropping any digit. We want to maintain the number of digits times 10 to the power. We moved this. This was only moved 1. So this is going to be to the power of 1. And then for this guy, now how many digits do we have here? We have 1, 2, 3, 4, 5. This is 5 significant figures of digits. And then if we're going to write the exponential notation, we have to maintain this digit. So it's going to be 7.0000, 1, 2, 3, 4, 5 digits times 10. If you look at this, we do not have to move this. And when you don't move it, this is going to be to the power of 0. So that is how you solve that problem. Any question at this point? You can always pause this video, practice these problems, and come back to them. All right, we have another one. Like, you can pause this video at this point in time, go through them yourself, and then get back and see what the answers are, so that you can compare them with what you have, and that gives you enough room to practice. So in this problem now, say we should state the number of significant digits in each of the following. This is a trailing zero. The zeros are in between two numbers. Every number has significance. So let's count 1, 2, 3, 4, 5. So this will be 5 sig figs. What about this one? This one now, these are leading zeros. They are not significant. So what is significant is this one here. So it's going to be 1, 2, 3. So we're going to have 3 significant figures. This one is also a leading zero and have 1 digit. So it's going to be 1. This is also a buried zero. We're going to have 1, 2, 3. This is going to be 3. What about this one? You see this one? This is a leading zero. But in this case, a trailing zero. But this trailing zero has what? A decimal. Therefore, every number here is going to be significant. Let's count it. So it's going to be 1, 2, 3, 4, 5. Again, we have 5 significant digits. If you look at this one, we're combining. These are trailing zeros. These are trailing zeros at the back, leading zeros in the front. The leading zeros, no matter whether decimal or not, are never significant. So, but the trailing zeros are significant when there is decimal. So we're going to count. This will be 1, 2. This is 1, 2, 3, and 4. So we're going to have 4 significant digits. And again, for this one, the last but not the least, let's count again. Now, you see, we have a combination of trailing zeros and buried zeros. Remember, the buried zeros are less significant, the trailing are not. So we're going to count. This is going to give us 1, 2, 3, and 4. So we're going to have 4 significant digits in these numbers. All right. We're going to move on to the next one. So now, let's try to practice how we do mathematical operations. Now, for one of the things you must do for yourself in this class is to get a simple scientific calculator. I usually advise students in this series not to use the big graphing calculators that could confuse them. I will advise you to use a simple scientific calculator that will help you do the problems without getting into trouble. Now it says calculate and round off the answer to the correct number of significant figures. Just remember again that in this kind of problem, we are going to be looking at what? The digits. If you look at these two numbers now, this is multiplication. And the rule says in multiplication or addition, the term with the least number of digits will be what the answer will have. So if you take your calculator, punch this thing inside, you're going to get the answer. Just do it. You're going to get the answer 59. This is what your calculator will show you. This is calculator answer 895. Now, but if you count the number of digits here, let's count. This is, how many digits do we have here? We have 3 digits. How many do we have? 4 digits. So what it means, the final answer should have 3 digits. So I'm going to approximate this number to this. So what else is going to be is that, but since I'm going to drop these two, this is greater than 5. I'm going to increase this one by what? 1. So finally, my final answer will approximately be 59.9 to the appropriate number of sig figs. This is 3 sig figs. Again, this is 3 significant figure. Now, to do this problem, problems that have multiple operations can be a little bit challenging for students at times. And I advise students to do it easily and simply. Now, if you look at this problem, the first thing you want to do to your calculator is to punch 4.5 times 10 to the power 23 times 8.70 times 10 exponential negative 6. If you punch that into your calculator initially, you see these are multiple operations involved. Now, in this case, if you point this to number, if you look at this, this has 2 digits. This is 2 digits at this point. This is 2. This one has 3 digits. What it means here, we're going to apply that rule that says when you are multiplying, the one with the least digit we have. So what am I going to do? This is going to give me, up here, I'm going to have 3.915 times 10 to the power of 18. Now, see what I'm going to do. This is not commonly done these days, but it's important students understand that. Now, because here, I want my answer here, assuming this is only what I have to do, my answer is going to be in 2 digits. So what am I going to do? I'm going to remind myself about that digit by putting a line. I'm going to put a line telling me that, okay, I'm going to make sure that finally this will be 2 digits. And I'm going to go to the denominator. Again, I'm going to punch it in the denominator. I'm going to say this times this in my calculator again. Again, remember, this is 3 digits and this is 4 digits because this is a trailing zero, but because of the decimal it counts. So this is going to give me 1.6182 times 10 to the power of 26. Now, I hope you saw my 26. I'm going to write it very well. I'm going to make sure it is clearer so that you're going to see it. So this is 26. Now, again, my answer under here has to be in how many digits? It has to be in 3 digits because this is 4. What am I going to do? I'm going to go back there and take my green again and make sure that my answer is going to be in 3 digits. I'll count 1, 2, 3. So my answer here is going to be in 3 digits to remind me that my answer will be in 3 digits. So now I'm going to do the last operation. You're going to take your calculator again. You're going to punch in this number 3.915 times 10 to the power of 18 divided by 1.618 times 6182 times 10 to the power of 26. When you punch this into the calculator again, you're going to have this number. What you're going to have will be 2.419 times 10 to the power of negative 8. This is what you're going to have. Now, but remind you that you have 2 digits up, you have 3 digits down. My final answer should be in 2 digits. What it means is that I'm going to have my answer at this point and drop everything after that. And since this number is just 1, not up to 5, what is it going to be? My answer, final answer is going to be 2.4 times 10 to the power of negative 8. This will constitute the final answer I'm going to report. Now, I want to say this. Irrespective of the fact that I'm not going to be too strict about the number of digits in your calculations by the time we get into this class, I have to maintain that in chapter 1 that involved this significant digit and lab 1, we have to apply this just to understand and recognize this thing. But I'm not going to be strict when we go beyond that in solving problems. Again, this is multiplication rule. When we multiply these two things, this is 2 digits here, 2 digits. This is 4 digits. What it means is that my final answer has to be in. So if you punch this into your calculator, you're going to get this. And since I want my answer to be in 2 digits, what it means is that my answer is going to be in 2 digits. I'm going to drop every other guy here. So what it means is that my answer is going to be 5. This is not up to 5. Therefore, it's going to remain 5, 3. Since I drop this value, it's not going to be 0. So this will constitute the number of digits in my final answer. So my final answer is going to be 530. This is how we apply the knowledge of significant digits in various mathematical operations. So so you can pause your video once again and try to do these problems. And then after that, you can come back to them once again. So do the following addition and subtraction. So if we go there now, remember in addition and subtraction, we're not interested in the number of digits. Our interest is just what? Our interest is at the decimal place. So look at it. There's no decimal place here. So let's say there's 0 decimal place here. There is 1 decimal place here. And there is what? 1, 2, 3 decimal place here. What that is telling us is that after adding these numbers, I'm not going to have a decimal place. So if I add these numbers, I'm going to get 1510.905. This is what I'm going to get in a calculator point. Now, but if you look at this, because one of the terms doesn't have a decimal, that means it's the least decimal. What it means is that I'm going to round this without a decimal. And as I'm going to drop these numbers from here, I'm going to drop all these guys. So since this number is up to 5, I'm going to increase the last number here to be 1, 1. And this will constitute my final answer. If I also go here again, the same thing happens. The same thing will play out as well. The same thing is going to play out as well if I come here. So here is going to be, if you subtract the number again, the decimal row plays role. So this is 1, 2, 3, 4 decimal places. This is 1, 2, this is 2 decimal places. If I add this number up, or subtract it rather, it's going to give me 0.0996. what that means is that I want it to be in 2 decimal place. So I'm going to round this up. What it means is that if this is up to 5, if I put this here, of course, it's going to give me what? A 0. It's going to give me 10. So what it means is going to be a 0. I'm going to put 0 here, and the next one is going to be 1. And then this is my 0 point. So my final answer is going to be 0.10. You should understand that this thing changed because this number was already 9. So it's going to increase the number as you move to the left of that. And this becomes our final answer. So this is how you apply the knowledge of significant figures to various mathematical operations. One last thing I usually decide to bring in, which usually I don't have to, is the percentage, bringing in percentage. Most of the things we're going to be doing will involve percentage. We're going to apply it. So I just want to remind you that percentage simply means the part over total times 100. It's just expressing every number as 100. So if you have this question, it says a student counts the money she has left until payday and finds she has $36.48 before payday, and she has to pay an outstanding bill of this. It says what percentage of her money will go to the bill. So the percentage here is going to give us the part of the money she's going to use in paying the bill will be 15.67. 15.67 over the total. She has a total of what? 36.48. You're going to multiply that by 100, and that will give us, what does that give you? If you punch that into your calculator rightly, you're going to get a number of 42.96%. That is the number you're going to get. Let's go to the last one. Another percentage problem, which will happen to be the last problem for this section. So a college has 4,517 female students and 3,227 male students enrolled. What percentage of the student body is this? So the first thing we're going to do here is that we're going to get a total number. Of course, don't forget the total was not given in this case, so you have to punch that into your calculator and get it. So it's going to be, the total will be adding this. So the percentage, I'm going to just write all of them together, will be, we're looking for the percentage of the female student. That's what we're looking for. So what percentage of the body is female? So it's going to be, the part of the measurement will be 417 divided by the total. The total will be 4,517 plus the male student 3,227. If you divide this, you're going to add this, take this, divide it by the total you got here, times it by 100, and at the end of the day, we're going to get 58.33%. So you should be conversant with a little bit of this math concept, because this will form the foundation for proper understanding of this class. At this point, I'm going to call it an end to this section again. We have one more section of this lecture for chapter 1 to end. I do implore you to watch this video as many times as possible and try to practice solving these problems yourself. Thank you very much for listening. I will see you next time. Have a wonderful day ahead of you.